So, thank you, Chairman, again for your introduction. Okay, perfect. Yes, thank you. The title of this presentation is the low-power pixel-level circuit for high-dynamic range time-of-flight camera. Also, in this case, I will try to briefly introduce to the problem, and then I will show you the solution we adopted. So, in particular, I will explain in detail the pixel schematic, together with some simulation results, some preliminary measurements and conclusions in the end. So I don't want to spend more words about that. The Professor Charbon showed us before. So the main problem related to this type of cameras is the presence of background light, which can influence the 3D measurement. So the work is based on the lock-in pixel that also Professor Charbon showed us before. So basically, the transfer gate, when we apply basically a voltage difference, can create a potential profile which basically forces photo charges to be detected by one of the two floating diffusion, D1 and D2. So the effect of the modulation of the demodulation of the light is that basically we can detect two types of contributions. The first one is the differential mode signal, which comes from the demodulated signal, and which can be observed by the different slope of the floating diffusion, and that which is the useful signal we want to detect at the end of the integration time. But the second contribution is due to the common mode signal coming from the background light, which cause the signal to saturate before the end of the integration time, losing this way the useful information for extracting the phase shifting we need for the test distance measurement. So exist in literature different approach in order to increase the dynamic range of a camera. Also, Professor Charbon showed us some example. But the basic principle is to introduce a sort of refresh operation for the pixel in order to reset the pixel in a periodical way, but still maintaining the differential signal to be accumulated during the integration time. So I want to underline two types of approaches. The first one is the pixel level approach. By means that it's possible to achieve, I think, the highest value of dynamic range boosting. But on the other hand, as the problem that has a very large pixel size. On the other solution, which is really interesting, it is an architectural level, what I can say, an architectural level approach, where part of the electronic is implemented into the pixel, part of the logic is implemented outside the focal plane. So in this way, the refresh operation has to be executed by selecting the pixel and read out the pixel, and for that reason, the frequency of the refresh operation is limited by the resolution of the sensor and also by how fast is our readout circuit. So basically, another important parameter to take into account is also power consumption, which is usually quite high in both cases. So the proposed solution was to be a first example of pixel level circuitry for background compensation, enabling a very compact pixel size. We are talking about 10 by 15 micron, and with fast computation, so achieving potentially very high dynamic range boosting, and also a very extremely low power consumption. We estimate a value of about 60 nanowatt per pixel at 10 kilohertz of refreshing operation. So to give you an idea, this is the pixel we realized in 2010 using a 0.18 micron technology, and this is this pixel we realize now, adding extra circuitry using the same technology. So which is the idea behind? The idea is to try to periodically interrogate the pixel in order to see if the maximum between VD1 and VD2, which are the two floating diffusion, is lower than a fixed threshold. Then if this condition is satisfied, we want to apply a refresh operation in order to accumulate the differential signal during the integration time. So how can we do that in CMOS, into the pixel level, at pixel level? So we start from the very simple pixel schematic. We have two transistors for resetting the two floating diffusion VD1 and VD2. And we have also two source followers, MN1 and M2, which are used actually to read out the pixel through the bit lanes. So we added few transistors in order to implement a maximum detector. And this can be done through the use of other two transistors, MN3, MN4, which are driven by the signal COM. And COM is high. These two transistors allow us to basically shortcut the source of these two source followers in such a way that VCOM is equal to the maximum between VD1 and VD2 minus the threshold voltage of the transistor. Then the other stage is another source follower, PMOS source follower, which is also in this case basically switched off during the integration time, and is enabled for a very short time in order to replicate this voltage to this node VO1 and VO2, which are exactly a replica of the maximum between VD1 and VD2. Then the final stage is a charge injector. The charge injector basically is consists by these two PMOS, MP1 and MP2, which has the source are shared between and connected to a reference voltage, Vres. So as soon as VO1 is lower than a threshold, than this value, there is a current flowing to two branches. So if this current is flowing, also the two floating diffusions start charging, so goes up. But if these two goes up, also VCOM goes up, and also because of the feedback, also VO1 and VO2 goes up the same way. So this process will term when VP1 and VP1 and VP2 will be switched off, and allowing another integration, still maintaining the differential value. Also, the charge injector has also two other transistors, these two, which are a cascade transistor in order to make this process independent of the value of VD1 and VD2. So this is the simulation result. As we can see, there are plotted two different cases, high and low background light, and with and without the compensation circuit. As we can see, as soon as in this case, the standard, the pixel saturates very early, while in the other case, you're still maintaining during the integration time the differential information. This is a very simple model I use in order to understand how is the boosting of the dynamic range, taking into account ideal, component. And this is the equation I found. Is really easy, which depends actually on how often I want to refresh the pixel. So looking at the measurement, I will firstly want to understand which is the behavior of the pixel, and this is the actual measurement I did. I forced the two transfer gate to have a different voltage in DC, and what I have here is the output of these are the two floating diffusion, which saturate quite early during the integration time. So applying the compensation circuit, we can see that the circuit, the pixel, behaves quite well. The pixel is also implemented inside to an array of 80 by 160 pixels. So what I would like to show now is the dependence of the distance measurement on the background light. So there is the sensor, and in front of the sensor there is a target, and also I put a light with variable intensity, which is project a sort of spot on the image, and then I take this portion of image in order to understand how the dependency of the distance on the background light. So this in red is the behavior of the standard pixel, which actually drops the value quite early into the 100 lux. But applying the compensation circuit, we can see that we extend the dynamic range of the camera. But the main problem that we can see now is that applying more higher frequency, the dynamic range that I can obtain is lower than we expect. So this is the problem is due to the fact that the signal amplitude actually is also reduced by the effect of the compensation. So this is the main problem that I encountered. Basically, this reduces the accuracy of the measurement actually the impossibility it's not possible to use to higher frequency. This is an example of 3D, real 3D image. This is in the case of dark. In front of the sensor there is different object. This is in the case of dark without compensation. This is in the case of illumination condition, but using also the compensation circuit. As we can see, the accuracy of the measurement is reduced by because of the circuit. So, as conclude, we demonstrated that it is possible to implement pixel-level circuit in order to extend the dynamic range of the camera. We also demonstrated that this we measured that this is feasible for low frequency, but also we also understand that there are some few problems to be better understand and investigate in the future. Thank you.